Welcome to this lecture on examples of calculations of expectations. There are two different lectures this week on examples. One example will be with respect to continuous distributions. How do expectation calculations look like for continuous distribution? We will primarily look at expected value of x, expected value of x squared, variance of x, those kind of calculations for some standard distributions, or also maybe some slightly non-standard distributions, just to show you how the calculations will look like. And then maybe I'll give some one or two interesting examples in the continuous case. And also in the discrete case, we'll primarily focus on a situation where the distribution might be difficult to compute, but the expectation is easier to compute. And that is a very important theme in this idea of using expectations to deal with random variables and random phenomena. Okay, so let me get started. Let's take a distribution, a very simple distribution to start with. Let's say x is distributed uniformly in the interval 0 to 1. Okay, so this is an easy distribution. If you want to draw the PDF fx of x, PDF, it looks like this: 0 to 1 and 1. And Professor Arvind did this calculation in the lecture. You know that expected value of x is half. Okay, so this is easy to do. How do you do this calculation? It's basically integral 0 to 1 x times fx of x dx, and fx of x is just 1, so this is just integral 0 to 1 x dx, and that's x squared by 2 evaluated between 0 and 1, and that will come out as half. Now what will happen to expected value of x squared? This again, if you want to do the same calculation, you want to do 0 to 1 x squared fx of x dx, and that is just integral 0 to 1 x squared dx, and that is just x cubed by 3, 0 to 1, that is 1/3. Okay, so what is variance of x? It's expected value of x squared minus expected value of x whole squared. So this is 1/3 minus 1/4, which is 1/12. Okay, so you might know some standard formulae which will give you these answers. I'm not saying this is the way to do it, but this is just a very simple prototypical example of computing mean, second moment, and variance. Okay, so this is called mean or expected value of x. This is the second moment. This is the second centralized moment or variance. Okay, so these calculations are what people call as bread and butter calculations. Given any PDF, you should be able to do this. So let me take one slightly non-standard PDF, and this will also give you a lesson on how to think of PDFs. So now, if I want a PDF which is, say, a line from 0 to 1, what should be the height here? Okay, so that's an important question to determine. What should be the value here? So it turns out the correct answer there is 2. Okay, and what is this equation? This is 2 times x. Okay, so that's a straight line which is 2 times x, and this will be a valid PDF. You can see that this is a valid PDF by integrating. Check for validity. Why is this valid? You integrate from 0 to 1 2x dx, the actual PDF. This was just x squared evaluated between 0 and 1, and you get 1, and it's non-negative in the interval 0 to 1. So this is a valid PDF. So this is a slightly different PDF from the uniform case. Higher values are more likely. Okay, so this is a simple PDF. So these kind of problems are also quite standard. Given a PDF, how do you make sure it's valid? Okay, how do you check that it's valid? How do you find some constant so that it's valid? It basically has to integrate to 1, and it has to be non-negative. Okay, so if you want to repeat this calculation here, if you want to look at expected value of x, how would you do the calculation? You do 0 to 1 x times fx of x dx. By the way, I'm doing 0 to 1 because the range here is 0 to 1. Okay, so this is what gives me the range 0 and 1, right? So that's enough for my calculation. So this is integral 0 to 1 2 times x squared dx. So that just becomes 2 times x cubed by 3 evaluated between 0 and 1. So that's 2/3. Okay, so you see the mean here is larger, right? So uniform case, the mean was a half. 2/3 is going to be to the right of half, the mean is larger, and that's to be expected because the expected value, this distribution, the larger values occur with higher probability, so the expected value should be larger. Now, this kind of inference in this simple case looks very simple. I mean, what's the big deal? You know the distribution itself. So quite often what will happen in real life complicated problems is you won't be able to figure out the distribution. You'll only know the expected value, and you have to make some statements about what will happen to x, and those kind of things. It's intuitive to see what expected value represents, and all of those intuitions should be very clear to you. Okay, so you can also compute expected value of x squared here. It will again be a little bit more complicated. 0 to 1 x squared times fx, which is 2x dx. So that is 2 times x power 4 by 4 between 0 and half, and that is half here. And what is the variance of x? It's half minus 2 by 3 squared. It's half minus 4 by 9, right? So that is 5 by 18. Okay, so that's the variance. You can do check this calculation for yourself. Okay, so that's two simple examples of computing expected value and second moment and variance, and this kind of calculation is quite standard. So now if you have distributions involving exponential functions, then the calculation becomes slightly more tricky. So I want to show you, you've also seen some calculations in class. In many cases you'll have to use integration by parts, okay, to simplify your integral. So I think it's important to know integration by parts very well. So particularly when you deal with integrations involving exponential function, that becomes important. Also, I think you can identify some symmetries of the function, even symmetry, odd symmetry, and then quickly do your work sometimes. So for instance, here's an example in the Gaussian case. If you look at fx of x is 1 by root 2 pi e power minus x squared by 2. This is a standard Gaussian. If you do expected value of x, so now remember x is going from the entire real line, right? Minus infinity less than x less than infinity. Okay, the whole real line is here. So if you do expected value of x, you will get this integration, minus infinity to infinity, x times fx of x e power minus x squared by 2 dx. The first thing to check is this integral converges, and I think that's not too difficult to see. You can see that this integral will converge. And the other thing to check is that check for some symmetry. If you notice, this is odd symmetric. So this integral will actually evaluate to 0. Okay, right? So if you have an odd symmetric function, if you integrate from minus infinity to infinity and the integral converges, this goes off to 0. So that's easy enough to do. The other slightly more tricky calculation here is the expected value of x squared. You're going to have x squared times 1 by root 2 pi e power minus x squared by 2 dx. Okay. So in this case, it looks a little bit tricky. So you'll have to do, actually in this case, you have to do integration by parts. I'm going to show you how I do integration by parts. The way different people do integration by parts is different, but this is the way that I like to do it. So you do integral minus infinity to infinity, keep x here, okay, and then you will have the 1 by root 2 pi plays very little role here. Let it be as it is. And then x times, what you will have left is x times e power minus x squared by 2 dx. Okay, so now this part, one can identify it as follows: integral minus infinity to infinity x times b minus e power minus x squared by 2. Okay, so what do we mean by this? If you do this differentiation, you will get that, right? So you'll get minus e power minus x squared by 2 times the derivative of minus x squared by 2, which is minus x. So that will become the same as this. So these two are equal. Okay, they're equal. You can check that. So once you do this, you can do integration by parts. So this is how I like to do integration by parts. This 1 by root 2 pi will come as it is. And then you multiply these two guys. These are the two u and v, u dv, right? So what is integration by parts? It says integral u dv, some a to b is uv evaluated between a and b minus integral a to b v du, right? So this is integration by parts. You should remember this. So I'm going to evaluate minus x e power minus x squared by 2 between minus infinity to infinity, and then minus integral minus infinity to infinity minus e power minus x squared by 2 times dx. So this is my parts. Okay, so I've applied this to this guy and got parts. Okay, so this is integration by parts. Now this quantity, so x times e power minus x squared as x tends to infinity actually goes to 0. So it turns out this e power minus x falls to 0 much faster than any polynomial in x. So these are some things you have to remember. So x power n e power minus x, limit as x tending to infinity, is actually 0. Okay, so you can also put it as x tending to infinity, x power n e power minus x squared is 0. Okay, so what does this mean? So this basically says the way e power minus x falls faster than x power n with x. Okay, so this is the important thing to remember for any n. Okay, n could be anything, any positive number. Okay, so this is an important fact to remember. So e power minus x, it's an exponential fall. It's much faster than any polynomial fall. So this will go through. So immediately this minus x squared also, I mean minus x squared by 2, whatever you have, all of those guys will go much faster. This is an important result to remember, particularly when you have e power minus x squared. You can also do x tending to minus infinity, x power n e power minus x squared, that will also go to 0. Okay, so these kind of facts about functions are very important to know when you do when you evaluate this function. So when you now look at x times e power minus x squared by 2, whether you put infinity or minus infinity, I'm going to get 0. So this first part will just become 0. Okay, now only the second part is left, and notice what happens to the second part. If I actually simplify this, minus infinity to infinity, 1 by root 2 pi e power minus x squared by 2 dx. What is this? This is the PDF of Gaussian, right? PDF of Gaussian distribution with mean 0 and variance 1. So that's something you know. So this integral will simply be 1. Okay. So after all these calculations, we found that expected value of x squared is actually equal to 1 for this. So this is an example of how to do parts. I think Professor Arvind also mentions how to do parts very clearly in his lecture. So I think I gave you a different way of in which I write it down. Maybe I gave you more steps on how to do it. So some things like this you should remember. Typically when e power minus x appears in the PDF, you'll have to use integration by parts to simplify the expression. So hopefully this is clear enough to you. Given any other kind of problem involving these kind of PDFs, you should do that. Okay, so the next important thing to remember in calculations is quite often you'll have calculations involving multiple random variables. I just want to give one example of how to do that. So let's say you have x1 and x2 having some joint PMF 1 x2. Okay, so the way I like to picture this PMF usually is I draw a two-dimensional plot x1 x2. Okay, and then draw the region of support. Okay, so what is region of support? This is something very important to understand in any 2D PDF. The region of support is the set of all x1 x2 for which fx1 of f1 x1, this guy, is greater than 0. Okay, so we'll assume simple continuous distributions, and this all of this is easy to define. So the set of all values for which this guy is greater than 0. So this will be some region here. Okay, so some region like that. Okay, so in this region you should have a good handle on. Okay, so you should be able to describe the boundaries of this region. You should be able to do a two-dimensional integral over this region. All of these things you should be able to do. So for instance, if you have to find expected value of x1 x2, what would you do? You'll have to do integral over this region. So I'll call it ROS, integral over the ROS. Maybe I'll write on a double integral for your comfort. You have to do x1 x2, fx1 x2 of x1 x2, dx1 dx2. Okay, so how do you evaluate integrals like this? It just depends on The integral like this is evaluated depending on the region. It's not very easy to give a general formula. So maybe I'll take a very simple example to show you how this is done. So let's take a very, very easy example first. So in the first example, my region is just 0 to 1, 1 here. Okay, so this is my region of support. Remember, this is x1 and x2. This is my region of support. Okay, so I haven't told you what the PMF is, so I'll say uniform. Okay, so this is a very standard assumption. So you put a uniform distribution on this region of support. So you can see what the actual description is. Fx1, x2 of x1, x2 is actually 1 if x1 and x2 are between 0 and 1. It is 0 else. So this is x1, x2. Okay. So now if you want to compute expected value of x1, x2, I'm simply going to do an integral. x1 goes from 0 to 1, x2 goes from 0 to 1, x1, x2, right? Times fx1, x2 of x1, x2, dx1, dx2, the same formula, but I know this guy is now 1, right? So it's just the integral 0 to 1 x1 and then integral 0 to 1 x2. See, this integral will actually separate out, right? So you do x1 equals 0 to 1. You can first do the x2 integral, okay, and then do the x1 integral. This integral we have seen before evaluates to just half, right? And then you have x1, I'm sorry, I shouldn't forget the x1, half. So this becomes integral 0 to 1 half x1 dx1, and the half will come out, and then you will have an integral 0 to 1 x1 dx1, that's another half, so you simply get 1 by 4. Okay, so this was a very simple case, and you see in this case it is actually that expected value of x1, x2 is actually equal to expected value of x1 times expected value of x2. Why is that? Because this gives you the marginal PMF. What are the marginals? fx1 of x1 and fx2 of x2, they are both uniform in 0, 1. Okay, so you have to check this, you have to check the marginals, and once you check the marginals, you see that this guy is half, this guy is half, this guy is 1 by 4, and we have verified that the expected value of x1, x2 is this. In fact, this is actually a very trivial case. In this case, x1 and x2 are independent. So if they are independent, the PMF, the PDF itself factors. Okay, so notice what happens here. So since x1 and x2 are independent, you have fx1, x2 of x1, x2 is actually equal to fx of x1 times fx of x2. x1 of x2, x2 of x2. So in this case, this implies x1 and x2 are independent. Okay, so if they are independent, then obviously this needs to be true. It's very easy to see. Okay, so that's the kind of problem. So I'm going to complicate the problem a little bit to give you the next example, where we will look at again a joint PDF with the region of support. Okay, but I'll take the region of support as a triangle. Okay, so just like I did in the previous case, in the one-dimensional case, I'll take the region of support as a triangle, but now this is a very different plot, right? So this is x1, x2, and I will say uniform over region of support. Okay, so I'm going to consider a joint distribution which looks like this. Okay, think about it once again. x1 and x2 take values within this region and they are uniform. Okay, so for instance, so I can take a value here, x1 and x2 can belong here, but outside of this there will be no x1 and x2 value. Okay, so in this part on so only the shaded part in the triangle, x1 and x2 can lie in. Okay, so it's slightly restricted. It's very different from the previous picture where you had the entire square and x1 and x2 could take values anywhere there. This is within this region. Okay, so here you will see the calculations will change a little bit. The first thing to calculate is what is the joint distribution. Okay, what is the joint distribution and how do you describe this? Okay, so it is uniform, so it's going to take a constant value, but what will be that constant value? Okay, so there you have to do some careful description. So it will take some value for x1, x2 in the region of support, and 0 for x1, x2 outside of region of support. Okay, so this I know. Now what should be this constant? How do you determine this constant? You have to integrate, right, over the region of support, this guy, and equate it to 1. Okay, so this will determine C. Okay, so how do you do this integration? I need a description of the region of support. Okay, so to describe the region of support, I will first take x1 from 0 to 1. Okay, so if you notice, in the region of support, x1 takes values from 0 to 1. Now for every particular x1, okay, so what is this line? You should have a description of this line. This is x1 equals x2. So for every x1, x2 takes values from 0 to x1. So if we fix x1 in the range 0 to 1, x2 takes values in 0, x1. Okay, once I fix x1, x2 can take values only from 0 to x1. Okay, it cannot go outside of that. That's the constraint of this region. Okay, as opposed to a square, we have only a triangle. So once I fix an x1, x2 can go only from 0 to x1. Okay, now I can do my familiar integration. This needs to be, so this needs to be equal to 1. So let's simplify the LHS. This one is an easy enough integral. Okay, integral C dx2. So you will get integral 0 to 1, x1 equals 0 to 1. That integral is simply C times x1 dx1. This needs to be equal to 1, which implies, now this integral is also easy. C times integral 0 to 1 x1 d1, we saw that before, that's half. It's equal to 1, which implies C equals 2. Okay, so this is how you determine the constant. So if you want uniform over a certain region of support, you will have a constant which is different from 1. Okay, so this is 2. All right. So now let's try and find the marginals also. If you find the marginals, you will get a very interesting sort of picture here. So what's going to be the marginal? The marginal, if you want to really find f, let's say x1 of x1, I have to integrate out x2 from the equations, right? Particular x1, I have to integrate fx1, x2 of x1 over 0 to the actual range, right? So this will be x2 will go from 0 to x1, right? For a particular x1, x2 goes from 0 to x1. C is the value of the PDF. I've got to integrate over dx2. Okay, so this simply works out as C times x1. C we saw as 2, so it is 2 times x1. Is that okay? What is the marginal distribution? 2 times x1, and x1 takes values from 0 to 1. Okay, so the marginal distribution of x1 will look like this. It's the same distribution that I considered before, the triangle distribution. What do you think will be the marginal of x2? Right? So for x2, I have to integrate over x1. Right? So let's look at that. fx2 of x2. I have to integrate the same guy dx1. But what is the range of x1? If you look at the range of x1, right? If you fix an x2, this is also x2. This point is also, sorry. This point is also x2. So if I fix an x2, x1 goes from x2 to 1. Okay, so the range is different, slightly different. x1 goes from x2 to 1. Think about it, because notice that this is a triangle. The region of support is a triangle like this. Okay, if I fix my x2 here, right, this will also be x2. So for a particular x2, x1 can take only these values. Okay, it goes from x2 to 1. So this guy will actually be C times 1 minus x2. So C is 2, so 2 times 1 minus x2. So how does fx2 look? So it's 2 times 1 minus x2. If x2 is 1, it goes to 0. If x2 is 0, it goes to 2. So it will look like this. So x1 is much more likely to take larger values, x2 is much more likely to take smaller values, and this is the distribution. Okay, but are x1 and x2 independent? Not really, right? So if you do fx1 times fx2, so you notice fx1 x2 of x1 x2 is not equal to fx1 of x1 times fx2 of x2. Okay, so think about how it will look. So the left hand side, right? So the left hand side is what? This guy is, we have this description that it is 2 for 2 in the region of support. And what is the region of 0 outside of it? What is the region of support? You have to describe it carefully here. So one way to write it, this is one way to write it. Think about why this is true. So for every, so you fix an x1, x2 lies from 0 to x1, right? So one way to write this thing is to say 0 less than or equal to x2 less than or equal to x1 less than or equal to 1. Okay, so 0 else. Okay, so this is a succinct description of the region of support. Okay, it describes this region of support. This triangular region of support is described by 0 less than or equal to x2 less than or equal to x1 less than or equal to 1. Okay, for a particular x1, x2 takes values from 0 to x1. Okay, and think about why this is true. So this is in x1, x2, this is true. Okay, hopefully this is clear to you. Now what about this product? This product on the right hand side, what will it look like? Okay, so this will look very different. This will be 2 times x1 times 2 times 1 minus x2 for what values? For any x1 between 0 and 1 and any x2 between 0 and 1. Okay, and 0 else. So this will actually have a region of support. What will be the region of support for the right hand side? The region of support will actually be a square. This will be the region of support x1, x2. Okay, and it will be non-uniform. Okay, so it will be non-uniform in that region of support. It will take some two-dimensional function. Okay, so it will be non-uniform. Okay, so we see that there are two different joint distributions here. This is also a valid joint distribution. This is also a valid joint distribution. Okay, both of them have the same marginals, right? You can calculate marginal for both, same marginal, but the joint distribution is different. Okay, so this is a very nice example to look at how this can happen. And you can also check that the expected value of x1, x2 if you calculate. Okay, so let's do that calculation next. It's an interesting calculation also. Okay, it will be different from the expected value of x1 into expected value of x2. So we see here expected value of x1 will be 2 by 3, and you can imagine expected value of x2 will end up being 1 by 3. Okay, and if you actually calculate expected value of x1, x2, okay, you can calculate expected value of x1, x2 for two joint distributions, for fx1, x2 of x1, x2, this uniform in the triangle, and for the joint distribution fx1 of x1 times fx2 of x2. Okay, for this distribution the answer will be what? Expected value of x1, x2 will actually be the product of expected value of x1 into expected value of x2. You can check this. So you will get 2 by 3 into 1 by 3, which will just be 2 by 9. For this guy it will not be the same, it will be something else. So here if you do expected value of x1, x2, you actually have to do the double integral. You take x1 from 0 to 1, you take x2 from 0 to x1, 2, and then you do x1, x2, dx2, dx1. Okay, so this will be a different integral. So let's do x1 0 to 1, 2x1 will be outside, and x2 dx2 integral from 0 to x1 is going to be x1 squared by 2. Right? You can do that. So you have x1 power 4 by 4, 0 to 1. So this is 1 by 4. Okay, so we see clearly these two have different correlations, expected value of x1 into expected value of x2. So this also was meant to give you an example of how to do calculations with joint PDFs and expectations, etc.